Okay, getting into the first part of type 3 problems, we want to go back and reference our net ionic equations guide from the very beginning of this packet. When we're dealing with a weak acid and a strong base, we follow a specific pattern for the net ionic equation. It is HA representing the weak acid plus OH negative representing the strong base component, right? Every time that acid's going to behave as an acid, give up its proton. So OH plus H plus is going to give us H2O, and then that's going to leave us with a conjugate base, right? Noted as a negative. So let's get into it with example 1. What would that look like for HF, which we know to be a weak acid, and KOH? Right? HF is going to stay together as represented by HA. So HF is our HA in the generic example at the top, right? That's going to be added to OH negative. We listed exactly as it's shown. Okay, that is going to form H2O, and it's going to leave us with some conjugate base. Now, we don't just leave it as A negative. What exactly is representing A here? That's going to be the F of our weak acid HF, so F negative. Right, now we're going to get into step 2 where I need to find these new molarities, then I need to put them into our ICE table, right, that I'm using this net ionic equation to set up. So I've calculated those new molarities by taking the given molarity and volume of each piece separately, finding the moles, and then dividing that by the total volume, so moles over the total liters. Now, how did I get that number for the total? If you look over here on the right, I added 150 milliliters to the 250 milliliters, excuse me, to give me a total of 400 milliliters. Remember, molarities in moles per liter, so I had to change that to 0.4 liters rather than 400 milliliters. So now I'm ready to take those new molarities that I found for HF, which is 0.28. The OH negative or KOH came out to be 0.94, so I'm going to plug those into it. So now that I've got our new molarities listed in the ICE table, remember I want to subtract the smallest value from both because that represents our limiting reactant, because one of them has to go to 0. So for this example, it is HF, because 0.2 smaller than 0.94, so that leaves me with 0. And 0.94 minus 0.28 is going to give me 0.66. Right? Now, what have I just found? I've just found an OH negative concentration. So remember, POH is the negative log of the OH negative concentration. So I can take that value now and use that in order to find our pH value. Now, here's the trick. So because the base is in excess, if I were to look at that titration curve back from the very beginning, right, I am most likely looking at a point well beyond our equivalence point, right, in which we now have a greater concentration of base than we do of acid. I'm expecting a basic pH for this one. So definitely something above 7. Right, so for this one, I'm going to take the negative log of 0.66. Right, and I get 0.18 for our POH. 14 minus that value is going to leave me with 13.82. Very basic pH. And that is our final answer. Okay, moving on to example 2. We have weak acid, strong base. So we're going to go through those same steps again, but we do have a different acid. So our net ionic equation is going to look a little different this time, but we're still following that same pattern. So remember, every time it's a weak acid and a strong base, right, mixture added together, right, our formula is HA plus OH negative yields water plus that conjugate base. So what is that going to look like for this particular equation? Our HA is our weak acid, it stays together. That's supposed to be a 2 there, my apologies. Plus OH negative yields water plus our conjugate base. Now what's that going to look like? That's this portion where we remove an H from the weak acids. That will be C2H3O2. We're going to give it a negative sign. Okay, so we're going to follow the same steps as we did last time. We're going to calculate those new molarities, and then we're going to plug them into an ICE table underneath this net ionic equation. Okay, so I've calculated those new molarities by taking the given molarity, multiplying it by the volume of each one after being converted to liters, got the moles, and then divided that by the total volume I got by adding both milliliters together, right? And then remember, we had to convert that back to liters before we could divide. So for our acid concentration, I got 0.33. For our hydroxide concentration, I got 0.067. It's a significant difference between those two values. So I've plugged those into my ICE table. As you can see here, from acid, I've got 0.33, which is much bigger than OH negative, 0.067. So I'm going to subtract our smallest. We have no hydroxide left. We have plenty of weak acid left. If I were to take a guess at where this is on a titration curve, this is going to be somewhere before your half equivalence point, definitely way before your equivalence point, because we've not added a whole lot of OH negative yet. Okay, so how does this problem differ from this point as we move forward? Well, we have an excess of weak acid. We have no OH negative, so I can't just do the negative log of OH negative because there's 0 of it. So mathematically, we have to approach this differently. So we've got a couple of options. You could set up a K expression. We are given a Ka value, or you could do an HH equation. Now, in example 1, an HH equation would not have worked because we have passed the buffer region, right? Remember, at that point, we were at the very end of that titration curve, right? We had went beyond the equivalence point. Now we're prior to that, so we're still in that buffer region, which means we can use an HH equation because we are dealing with a buffer here. Now, how do I do that? If I want to use the HH equation, I need two numbers. Where do I get that other number from? Now, we didn't need to go through this step in example 1, but we are going to do this in example 2. We're going to look at the other side of the equation. Remember, we're not worried about water. It's a pure liquid. It's not part of our K expression. But this started with none of our conjugate base, right? And we added 0.067 to it, right? So its new concentration is 0.067, the exact amount of the OH negative that we subtracted. So now I've got information I can work with. So from the HH equation, I know pH is equal to pKa plus the log, right, of my A negative over my HA concentrations. Definitely want to use those. So from there, pH is equal to the negative log of our Ka, right, which is 1.9 times 10 to the negative 5, because that's given in the problem, plus the log of 0.067 divided by 0.263, our acid. All right, so we're going to plug that in our calculator. Okay, once I type everything in, I get that our pKa is 4.72. I type in that log, I get a negative number. Sometimes that happens, that's okay. You can type that whole thing in at once if that scares you. So you get it all together. Your pH value ends up being 4.13. That is the final answer for example 3. You'll need to jot this down because this wasn't given to you on the original handout. So still have a weak acid, we still have a strong base. The difference is, if you'll notice, you have the same concentration in the same volume. Now, perhaps you're given concentrations that look a little different with volumes that equate so that you get equal moles. Regardless, what I want you to notice as we move forward is this is equimolar, which means for us that this point occurs at the equivalence point on our titration curve, because that's where the moles of acid equal to the moles of base, then they all react, right? Which makes this problem mathematically a little more challenging than the others we looked at. Following similar steps, but we're going to have several extra steps on the end. Let's get into it so I can show you why. First thing we're going to do, like always, write that net ionic equation. Let's find those new molarities. Let's get them into that ICE table. Okay, first things first, HNO2 represents our HA. It's going to form water, and our conjugate base is going to be NO2 negative this time. Right, so let's work on getting those new molarities next. So as we're approaching this problem, we've found the new molarities both for the weak acid and the strong base, and I've plugged them into the ICE table. And now our next step is to subtract the smallest number, right, from both of those values. The problem is that they're equal. So the smallest number is the number. So minus 0.1 minus 0.1, and it was 0, and it was 0. Okay, now what? How am I supposed to get a pH from here? We've got to go back and rely on that conjugate base because we can't rely on the water. Remember, it can't be part of the K expression, so it can't tell us anything here. So what I'm going to do is I know that our X is 0.1, so that is added to our NO2 concentration. So its final concentration is 0.1 molarity. So here's where it gets a little tricky. Now I'm going to have to set up a new ICE table because at this point, the only thing floating around right inside our beaker is conjugate base and water. There's nothing else in there. So what's going to happen? How is that conjugate base going to react with water? Since those are the only two species left. So let's write a new equation, which is backwards of this net ionic equation we have above, right? So let's flip it. So our NO2 negative and our ICE table is 0.1 plus water, which is going to behave as an acid in this example. Okay, and we are going to get HNO2 plus OH negative. Okay, so I know that this one is 0.1. This time I have no idea what X is. No clue what's going to happen. So that's where we're going to start, right? So 0.1 minus X. So our E value here, we're starting with 0 plus X, right? Our values of X. I forgot to give you that Ka value for HNO2, so let me back up for you. The Ka here for HNO2 is 4 times 10 to the negative 4, 4.0 to be exact. Okay, so now that we have that, let's get back into it. Right, let's figure out what X is so that then we can set this up in an expression. All right. Here's where this problem gets even trickier. The ICE table's filled out. We're ready to put those numbers in a K expression and solve for X. We know that K is the concentration of products divided by the concentration of reactants. The problem with this is that we're given a Ka value, that's for an acid, but nowhere in this equation do we have an H plus to work with for that Ka. So the problem here is that our X, what we're finding is actually an OH negative. So we're at a point because the only thing that we're dealing with in the beginning is a conjugate base. So instead of a Ka, we need to plug this into a Kb expression. Well, how do I get Kb? So remember this equation? Kw is equal to Ka times Kb. We need that right now. Kw is a constant, 1 times 10 to the negative 14 at room temperature, that is, right? That is equal to our given Ka value, 4 times 10 to the negative 4, right, times Kb. When I solve that, I get that Kb is equal to 2.5 times 10 to the negative 11. So that's the number I need to use in this expression, Kb. So 2.5 times 10 to the negative 11 is equal to x squared. So products are x times x over 0.1. From there I solve for x and I find that x is equal to 1.6 times 10 to the negative 6. Molarity. Remember that x is equal to HNO2 and OH negative. Which one of those two things is going to actually help me to get a pH? It's going to be the OH negative. All right, from there, I can take the negative log of 1.6 times 10 to the negative 6. Remember, that's our OH concentration. That's what I'm taking the negative log of. Okay, and that's going to give me our POH. All right, so when I take the negative log of that value, I get 5.80. 14 minus 5.80 to get my pH. I end up with a value of 8.20, which sounds right to me because I'm expecting a basic pH. Why? Because we only had that conjugate base present after that first ice table was finished. Okay, last section. Moving on to type 4, weak base and strong acid. Notice we're going through the exact same steps as we did in type 3. We're going to write that net ionic equation, get new molarities, do the ice table, subtract the smallest x, and then we have to figure out from there, based on which one's bigger, what our next approach is. So extremely similar to what we did before, and I'm going to roll through this one much more quickly with you. Let's get started on example 1. Okay, so example 1 for type 4 is just like example 1 for type 3, except this time we're dealing with a weak base, right? And a strong acid. So now that I've found those new molarities, I've plugged them into an ice table. I am subtracting the smallest number from both of those originals, so I have no weak base left. I have H3O plus, which remember is the same thing as H plus. I have that in excess, which means I have more acid than base present. So from here, it's pretty easy to calculate our pH. We don't need to do an HH equation, and we actually can't because this isn't a buffer situation. We're outside of that buffer capacity. We're actually beyond the equivalence point in the titration. So here, I can simply take the negative log of that H3O plus concentration, and I've got the pH, which is really acidic at 1.10. Moving on to examples. Okay, so now that I've found the new molarities and plugged them into the ice table, I see that I have 0 H3O plus left. I do have some of that weak base left, right? The CH3 and H2 of 0.575. What that tells me is we are in the buffer region because I have more weak base than acid. That means we're starting here with a weak base on this titration curve. And I am somewhere, didn't mean to make that circle there, guys. I am somewhere between this point and this point before we hit that big steep hill down, right? So I'm in that buffer region. So that means that I can use the HH equation because this is still acting as a buffer. So that's going to make our math a little easier because we don't have any H3O plus. I can't just take the negative log of it because I don't have any at this point in the titration. So only difference is my HH equation is for a base this time. So instead of pH, I set it up for POH, right? And it's equal to pKb rather than pKa. All right, plus the log of the conjugate acid concentration over the base concentration. Right? So I've got those numbers, I get those plugged in. That gives me a pOH of 1.99. 14 minus that pOH leaves me with a pH of 12.01. I want to circle back real quick to the net ionic equation up here just to make sure you guys are following me. So the net ionic equation for these is the weak base, right? Your weak base, it's always plus H3O plus. How does that work? Well, our acid over here, right, we're only worried about the H part. Since we're adding strong acid, the NO3 part of it is going to be a spectator in this case. So you won't see it come back up. So it's acting as the acid. So we move to the right side of the equation on our product side. We're taking one of the H's away from H3O and adding it to that base. I chose to put it on the front here. If you had made it H3 on the end and left your plus sign, it's totally fine, completely acceptable. Does not matter which way you choose to go about it, okay? Make sure we do increase the charge by 1 though, because it did accept a proton. And again, water's not part of our K expression, but we do need to note it here if we're using H3O plus in the equation. All right, moving on to example 3 and our very last problem. Okay, guys, go ahead and take a second and write this one in because it was not included on your original equation sheet. First thing I want you to notice is that we have an equimolar situation again. And these require the longest math. They're not super hard, they just have more steps than the others. So take a second to write that down. Let's get into it. Okay, so I've calculated the new molarities of both because these are equimolar. We've given the exact same numbers for both of these. It's really easy to calculate, so I got 0.05 for both. So I've plugged those into the ICE table that we set up. It's the same ICE table as an example 2 because we're dealing with the same weak base, and it's reacting with a strong acid. I did add our 0.05 on the right side of the arrow for that conjugate acid, can include water. So here's the problem. I can't take the negative log of the H3O plus because that number is 0, so that won't give me the pH. I can't do an HH equation because I don't have any of the weak base, so I can't do that setup. A K expression isn't helpful right now. I simply don't have enough information. So what I've got to do is consider that now that all of my acid is reacted, all of my base is reacted, now I've got to see what effect this conjugate acid is going to have on the solution. So this is one of those points where I've got to do that second ICE table. So what I'm going to do is rewrite the exact same net ionic equation, but I'm going to flip it. So I'm going to start this time with the HCH3NH2 plus water. Remember, I'm just flipping it around, CH3NH2 plus H3O plus. Because I know that that amount of our conjugate acid is going to have to react with water, and it's going to have to produce some weak base. Right, so I'm going to do another ICE. And this time I'm going to put that 0.05 as our initial, subtract x, 0.05 minus x, right? Leave out the water, 0, 0. We're going to add x for both of these, giving us x. Now this is that point where we want to set up a K expression so that we can solve for x and we can finally figure out what the pH is. We're running into that problem again. We're given a KB. Okay, when I set this up, I don't have a base to solve for on our product side. What I do have is an H3O plus. So we actually need to switch that KB to a Ka value because that's more appropriate for where we are because I only have conjugate acid right now. I don't have anything else. So I really need a Ka. So what I'm going to do, right, is go back to that Kw, right, it's going to save us, is Ka times Kb. 1 times 10 to the negative 14 is equal to Ka times 4.4 times 10 to the negative 4. I'm going to solve that, get an answer for Ka. Once I plug that into the calculator, I get that our Ka is equal to 2.3 times 10 to the negative 11. Now I'm ready to set up that Ka expression. So Ka is equal to products over reactants, so I get x times x over 0.05. We're going to neglect that subtraction of x to avoid a quadratic. Once I solve this and take the square root, I get that x is equal to 1.07 times 10 to the negative 6. Okay, so which of these two values is actually really helpful to me in order to find a pH? It's going to be that H3O plus. So if I take the negative log, that's equal to H3O plus, right? So I take the negative log of that value, and I get 5.97. Is equal to our pH, and that is our final answer. All right, that concludes all of your math and calculations dealing with buffer problems. I've got a few questions at the end here I want you to answer for me, and then you will be free to go. Here are those last questions. See if you can jot those down and then answer to those somewhere at the end of your packet.